So this video will cover the force notes that we'll take, force and Newton's laws. Um, so up at the top, we've got the equation for how we would calculate force. We're not going to be doing a lot with this, but this equation is actually helpful to understand all the components of force and what makes it work. So force is mass times acceleration. So basically how heavy an object is times how quickly it's speeding up or slowing down will determine the force. So another word for force is push or pull. And when we're thinking about mass, what we're talking about is the object, right? How heavy that object is. Usually when we're talking about how heavy it is, generally heavy things are also bigger, but let's not confuse heavy and big, right? Those are not necessarily the same things. So push or pull, mass is the same thing as object, and acceleration is just motion, right? So really what we're talking about is force being a push or pull on an object in order to get it to move or to stop moving, right? You might apply a force to an object, like you might use a baseball bat to hit a baseball to change the direction of that baseball and to get it to move towards the outfield rather than towards the catcher. You also might use a baseball glove to catch that ball and stop its motion. So depending on how you apply the force to an object, you'll either start it in its motion, stop it in its motion, or change the direction, right? And obviously a change in direction causes it to quickly slow down and then reverse and speed up in the other direction. So we often refer to unbalanced, balanced, and net forces. So an unbalanced force is a force or combination of forces that are not equal in size or direction. So think of a one-sided tug of war, either where there's just, 5 people versus one, that will be very unsided, and you're going to have an unbalanced force heading in the direction of those 5 people who would likely win. Sometimes an unbalanced force is just you picking up a box or you pushing that box along the floor. There are other forces at work, whether it's friction or gravity or those kinds of things, but you being able to pick up the box or slide the box, you are winning. So that would be the unbalanced force. Balanced forces, on the other hand, are balanced. It's when those two or more forces cancel each other out, both in size and direction. So the object doesn't move when there's balanced forces. So it's an equal tug of war. That rope doesn't move left, it doesn't move right, nobody wins. So when you have an unbalanced force, you're going to see motion happen, right? You have a one-sided tug of war, that rope goes to the winning side, and the losing side gets dragged along with it. When it's a balanced force, there's no motion. So net force is the total combination, it's the total combined forces acting on an object in all directions. So sometimes those cancel each other out when it's balanced, or other times it's unbalanced and you'll see motion. So often there are multiple different forces acting on an object. There's gravity pulling you down. You might be pushing your body up, or you might be pushing another object up in one direction. The wind is pushing it in another direction. Gravity's pulling it down. So net force is kind of trying to capture all of those different forces in all of the different directions happening. Friction is a force that we're all very familiar with. It's one of the most common opposing forces. There are two main causes of friction. One is surface roughness, and the other is force of contact. Surface roughness is how rough the surface is, right? It's the size of the microscopic hills and valleys of any surface. And the bigger those hills and valleys, the bigger those bumps, they will interlock more often. They will get stuck. So think about using sandpaper, right? Taking normal paper and rubbing it along the table versus sandpaper and rubbing it across the table. That sandpaper, because it has bigger bumps, bigger hills and valleys, it will sand off the table that you are rubbing it against because those hills and valleys get stuck onto the hills and valleys of the wooden table. Force of contact is basically a fancy term for how hard you're pushing two surfaces together. It is often caused by more weight. So if you have a box on the floor, if that box is not being pushed very hard against the floor, you can slide it very easily, right? Thinking about an empty cardboard box, for instance, right? That empty cardboard box, the two surfaces, the floor and the bottom of the box, are not coming into great contact. But if you push down on that box, either because you're standing over it and pushing it down into the floor, or because you add a bunch of books into it, so now it's much heavier, those two surfaces, the floor and the bottom of the box, are coming into contact. The more contact that there is, the more the hills and valleys, right, the microscopic bumps of the box and the floor come in contact and they get stuck on each other. So in both cases, what we're talking about is increasing how much contact or how much touching is happening between the two surfaces. And friction will often cause objects to slow down or stop moving, or keep them from moving at all. People often think that surface area is a cause of friction, but what we will find is that it is not a cause. Because while there is more touching, right, the more spread out an object is, there's more contact, there is less pressure or force of contact in any one area because that original force is now spread out across the larger surface area. So surface area, not a cause of friction. There are two main types of friction. There's static and there's kinetic. Static friction is friction that's acting on objects that are stationary. They're not moving yet. It's what keeps things from just sliding all around all the time. When you put a book on a table, that book doesn't just slide off the table randomly. And that's because there's friction interacting between the table and the book. You would need to accidentally bump or push that book in order to get it to slide off the table because of static friction. Conversely, if you're up in space where there's no gravity and therefore there's no friction, if you put an object kind of on a table, it's just going to float or slide away because there's no gravity holding it in place, which means that there's no friction between those two surfaces because there's nothing forcing those two surfaces to come into contact with each other. Kinetic friction is moving friction, right? It's friction from moving objects. There's three subcategories: sliding, rolling, and fluid. Sliding, shocker, it's when two objects rub against each other. They slide against each other. Rolling is when you have wheels, right? And those wheels of some kind or a ball is rolling over another surface, right? And fluid is when an object moves through a fluid, which could be air or it could be water. So air resistance is a type of friction. If you have a boat and you're calculating the resistance that that boat has, and you can get more, not aerodynamic, but water dynamic boats, right? Boats that slice through the water more efficiently. That is another type of fluid friction. Friction is caused essentially because of gravity, right? Gravity is the main cause of friction because it's causing objects to come in contact with the surface of the earth. Gravity is a force that pulls all objects towards each other. It is the other most common opposing force. It is only measurable with objects of planetary size and mass because those things, those planets, have enough mass to create a gravitational field. You and I weigh so much less than a planet, we effectively have no gravitational pull. So the amount of gravity depends on the mass and the distance of the two objects. What that means is larger planets, heavier planets, will have a greater gravitational pull. But if that planet is really, 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 really far away, it's going to have less of a gravitational pull on other things that are super far away. If two planets are close to each other, the closer they get, the more gravitational pull they will have on each other. So despite the fact that we are really far away from the sun is so supermassive, it has a big gravitational pull on us. The sun has less gravitational pull on Pluto because Pluto is so far away. It also doesn't help that Pluto is also very, very small. It is therefore very small in mass and therefore will also have less gravity. Free fall happens when the only force acting on an object is gravity. Right? That only happens when you are completely falling and there is nothing else other than gravity acting on you. Technically, that means no air resistance. So that would only happen in a vacuum, whether that's in a constructed vacuum like we have, like we watched in that video with the bowling ball and the feather, or whether that's in space. Because otherwise, air resistance is always acting on the object. We will often refer to free fall if things are just falling on Earth, but technically that's not free fall if there is air resistance. And when things are falling, right here it says falling at negative 10 meters per second per second. So again, that's a rate of acceleration. That's not the speed they're falling. But just like when we saw that the bowling ball and the feather without the air resistance, so in free fall, they both fell at the exact same rate, right? Meaning that they were moving right alongside each other. And so falling at minus 10 meters per second means that every second, a falling object without any air resistance is getting 10 meters per second faster. So if it's allowed to fall for 10 seconds, it'll be going 100 meters per second. And this is just the universal rate of acceleration due to gravity on Earth. It'll be different on the moon. The moon, I believe, is negative 1.6 meters per second, so about a fifth as quick, right? And that's because the moon is less massive. It has less mass, it has therefore less gravity, and therefore things don't fall as quickly on the moon. It's also why astronauts bounce around on the moon, whereas that doesn't happen on Earth. So all objects on Earth in true free fall, meaning no air resistance, will accelerate towards the Earth at minus 10 meters per second. The actual number is minus 9.8, but minus 10 is just a lot easier. So when we get into Newton's laws, these sound complicated, but in reality, they're really, really simple. Okay, so Newton's first law of motion can be summarized by the word inertia. The fancy way of saying it is that objects in motion stay in motion, while objects at rest stay at rest until another force acts on it. So in other words, stuff doesn't just start moving or stopping randomly. Something has to make it start moving or stop moving. Heavy stuff is harder to move than lighter stuff. Heavy stuff is also harder to stop moving than lighter stuff. Right? Think about somebody throwing a bowling ball at you rather than a tennis ball, right? So the other forces that might act on it could be gravity. It could be somebody pushing or throwing it. It could be friction, air resistance. Really, any force could be the thing that starts or stops the motion. But the important part is that motion doesn't just randomly happen, right? There needs to be that external force. And the heavier an object is, the more inertia it has. Inertia can't be quantified in terms of a number. That's mass. But we can describe things as having more or less inertia, which means that they will have more or less mass. So something that's heavier will have more inertia, meaning it's harder to get moving or to stop moving. Newton's second law, I always think, is the same as the first law, but it's just in math. So it says an object's motion is dependent on its mass and the size of the force applied. A heavier object requires more force in order to accelerate it at the same rate as a lighter object. A greater force results in higher acceleration. So all we're saying here is that big forces make an object go faster, and heavier objects are harder to move or accelerate, while lighter objects are easier to move or accelerate. Same thing goes for stopping their motion or changing their direction, right? It's easier to change the direction of a toy car than a real car, right? It's easier to push a toy car than it is a real car, right? So those things would require more force in order to get them to go faster. So again, pretty simple. And we can then play around with this equation, right? And you can actually calculate how much force would be required to move an object of a certain mass at a certain rate of acceleration, right? You could start plugging in numbers and doing math here and solving. If you knew how big the push was and you knew how quickly it was accelerating, you could calculate for the mass and vice versa. The third law is what we've always heard of, like equal and opposite forces, right? Every action has an opposite reaction, right? So if object A exerts a force on object B is going to exert an equal amount of force in the opposite direction on object A. And then in parentheses, it says the object with less mass will often be the one seen moving. So in other words, what we're saying is that equal and opposite forces in motion, reactions, both objects exert forces on each other and they both move, but we don't always see them both moving. So when I jump, I exert a force on the earth. Why don't I see the earth moving? That's because the earth is massive, and we mean that meaning it has a big mass, and you are tiny compared to the earth. So when you push on the earth, it does move a teensy tiny bit, but you are the one seen jumping, right, moving a lot. And that's because the earth weighs billions upon billions times more than you. And because the earth is so much more supermassive than you, it might accelerate, but that means it is going to move a trillionth of a meter, which is not something that we can measure. However, If we try this on the beach, you can see the earth move a little bit, right? The sand spreading apart and moving away from your feet as you jump on the beach or you run on the beach is showing that the earth is moving. It's just a little bit of sand is what you're able to move while you run forward or jump up in the air. In space or on a rowboat, however, you're going to see that opposite motion much more easily, right? As you take a dinghy towards the dock, if you jump out of a dinghy, that dinghy is going to fly backwards while you fly forward a little bit, but probably fall into the water or maybe slam yourself onto the dock. So here's a picture here where as this person pushes down on the surface of the earth, they're pushing down on the earth and the earth pushes back on them. Because the person weighs way less than the earth, the person is the one that we see moving. The earth isn't going to move because it's trillion times heavier than this person. If this was on the beach, we'd see some sand moving. That's the earth's motion. That's as much of the earth as you're going to move, right? But in general, the lighter object, in this case the person, is going to be the one that we see moving. In space, that's not going to be the case because there's no gravity at work here. So if the astronaut here pushes against a brick wall, that brick wall will move. It's not going to move as much or as quickly as the astronaut because the astronaut doesn't weigh as much as a brick wall, but that brick wall will move. If you push a brick wall on Earth, that brick wall is not going anywhere because it's way heavier and there's gravity, right? It's stuck to the ground. That brick wall is technically kind of a part of Earth at that point, right? Because it's connected to it. But in space, that astronaut pushes here, that brick wall will move away, but so will the astronaut. Will go flying backwards because there's nothing tethering that astronaut to the ground or anything. Same thing works when we're talking about a cannon and a cannonball, right? If you've ever seen a cannon fire, it's got a brace in the ground, right? For one thing, that wheel generally gets locked or it's allowed to spin backwards a little bit. The cannon definitely moves backwards, but the cannonball goes flying forwards. It goes flying forwards way farther and way faster than the cannon. The cannon moves a little bit backwards, and it moves pretty quickly backwards, but not as nearly as quickly forwards or as far forwards as the cannonball moves. And that's all because of the difference in mass, right? In here, there's a chemical reaction. That chemical reaction creates a huge force through the explosion, right? That explosion, a controlled explosion, forces the cannon backwards pretty quickly and maybe 5-10 feet, but it shoots the cannonball forward way faster and hundreds of times farther because this cannonball has a much smaller mass compared to this cannon. And so what we see here is the cannon shoots backwards, staying clear, but the cannonball flies forward at a much faster speed and goes much farther because it has less mass. So the same force pushing on the cannon only moves the cannon a little bit, but that force on the cannonball, which is way lighter, moves it a lot. So when we're seeing Newton's third law in effect, Newton's third law always happens. When you walk on the ground, you push on the earth. And luckily, the earth pushes back on you. We don't really think about this until we don't think about something pushing back. If the earth didn't push back, you would fall through the earth. When you go into the water, this kind of happens. If you walk off the ledge of a swimming pool, not realizing that you're no longer walking on the side of the pool, on the pool deck, but you walk into the water, not realizing it, it takes a while for that water to push back against you. Right? You can do it, right? As you go into the water, let's say it's a 20-foot deep pool or something like that, you won't just sink to the bottom. You're going to get pushed back up to the top. But it takes a little bit longer because it's a fluid, because it's a liquid that the molecules of the water take a while to push back up against your body, right? We're describing buoyancy, but that buoyancy is an upwards force fighting gravity. You fall into the pool and you sink a little bit because gravity is pulling you down. The pool water is pushing you up. It just takes a little bit longer for all those water molecules to push against each other and push back up against you, forcing you to go up. So we have felt what it's like for that reaction force to take a little bit longer. It's why running on the sand at the beach is harder, because you are now actually seeing the earth move a little tiny bit. So all of this is to say that force is how hard you push on an object to get it to move. Forces can be balanced or unbalanced. If they're balanced, we will not see motion. If they're unbalanced, we will see motion. We can think and look at the total combined forces, the net force. Friction is caused by surface roughness and force of contact, how rough a surface is and how hard you're pushing those two surfaces together. There's static friction for objects that are not in motion, and kinetic friction, which can be sliding, rolling, or fluid for objects that are already in motion. Gravity is what's causing friction. Gravity is what's causing all things to get pulled towards the center of the Earth or whatever planet you're on. And on Earth, when you're here, we're never really in free fall because we're not in a vacuum. We will experience air resistance. Newton's first law is inertia. Heavy stuff is harder to move, right? Lighter stuff is easier to move. And stuff doesn't just randomly start moving or stop moving. Newton's second law is how we can actually calculate the amount of force that would be required to move an object at a certain rate of acceleration. Once again, saying that if we want something to move faster, we need to push harder. And the heavier that object gets, we're going to need a bigger force. Newton's third law just describes how and why things move, and that every force exerted on something, that force gets returned back in the opposite direction by the other object. Right? It is why you're able to walk very easily on dry ground, right, on the gym floor, but not on the beach, right, because that action reaction force happens so quickly in space. Both objects will be seen moving much more readily than you would on Earth, where there is that gravity tying those two objects in place, and there's the friction, right, as you push against the wall, for instance.